Ladies and gentlemen, please welcome back to the stage Guido Appenzeller.
All right, so we got the second to last session here, and it's a topic that actually personally really interests me at the moment because as part of the big change in IT we're seeing with the movement to clouds and distributed applications, we're changing the infrastructure of how we build applications. And the architectural principle that seems to emerge is microservices, or I guess a hipster SOA, as somebody called it recently. And the tool of choice are containers. And that, I think, will have a very profound impact on networking for a number of different reasons. We're going to kick this off with Suneet Nandwan and Ashwin Raveendran from eBay, who are going to tell about their container deployments, one of the most interesting ones and of the largest scale overall deployments I've ever seen. Cheers.
Thanks, Guido. So just to introduce ourselves, so I'm Suneet Nandwan. I lead the cloud infrastructure and platform services team at eBay. With me is Ashwin. He's our lead architect for the cloud platform. So I'm just going to go ahead and give you guys a general overview of our cloud, and then Ashwin's going to go a little bit more deeper on the actual containers and networking aspect and where our challenges are over there. So some quick obligatory slides on eBay. I think everybody knows it pretty well, but a lot of people just know of eBay as just eBay, but it's actually a global business and has more than, and the main pillars of eBay as a company are, the eBay marketplace site, and then StubHub, some of you may not know, is an eBay company, and the eBay classified groups. Between everything, about $2.2 billion in revenue, 60% of our revenue is actually international, and 164 million buyers. So the scale, is pretty massive of eBay Inc. as an entirety. And then if you look at the marketplace business, which is the eBay main site as we know it, that's also pretty big. And that's really what, Ashwin and I, the cloud platform that we build and operate is really to serve this part of the business. And still pretty massive, 1 billion live listings at any point of time. It puts a lot of pressure at the infrastructure level, a lot of demands on our search platform, on our Hadoop analytics platform. So the scale of the real thing I wanted to show you guys this is not just from a, hey, what's eBay all about, but also just the kind of scale that we have to deal with at eBay. It's a really massive scale from an infrastructure point of view, and we have about several thousands of developers who constantly, developer experience, developer productivity is really, really important, infrastructure uptime. So all of those challenges actually our team has to deal with. I wanted to give you a quick overview of our private cloud, and then we will get more specific on that. So let's build this out. So really quickly, our first generation cloud, around 2010, we didn't have much to say in terms of automation. We built some homegrown tools to deploy applications on the cloud. Mainly we took some of our manual processes and build an orchestration layer around it. So you could take our applications now, deploy them on VMware-based ESX systems at the time. The journey really started, I would say, in about 2011, where eBay really started focusing on infrastructure automation. So this is the time we built out a lot of the foundational services which are still serving us really well. Bare metal provisioning services, DNS automation, load balancer automation, our ability to orchestrate, right, and a lot of the DNS automation. So there is a lot of stuff that we did at the infrastructure layer, and one of the things that we did pretty well at the time was we built a really solid bare metal provisioning layer, and this actually served us really well. So we are starting to move a lot of traffic. This journey happened in about from 2010 to about 2013. That was the second generation of our cloud. The second generation of cloud was an OpenStack-based cloud. And OpenStack, we are today one of the largest operators of OpenStack. They don't publish the numbers out there, but we've got like literally tens of thousands of machines on OpenStack. And the reason we went to OpenStack was community involvement. We are starting to look at things in a much more open source friendly manner. didn't want to solve all the problems by itself. We wanted to contribute and gain a lot back from the community. And one of the core things that happened while OpenStack was being operationalized at eBay was we actually started using SDN internally, mainly to solve a multi-tenancy problem at a macro level. So we wanted to do segmentation and isolation of the networks, and we looked at how to do it, and so SDN was the way to go. And we were one of the early adopters of NSX. I think we were one of the first largest customers of NSX, and anybody who's on the NSX team in those days probably knew us all by first names because the amount of communication we had at that time. I think the part where it gets really interesting is on the Kubernetes side. So one of the things, let me actually just fast forward this. I think the third generation of a cloud, I would say, probably started this year when our Kubernetes journey started. So last year, we started doing a lot of POCs and experimenting with Kubernetes. We tried Mesos, we looked at a lot of different things, and then we settled that we made a bet on Kubernetes. And this year, we really started to ramp up that program. And that's why I'm calling it our third generation. And I'm going to skip some of our starts of our cloud. A little bit about why did we really need Kubernetes in our environment. So this slide is pretty illustrative. You see it's filling out, right? So the two boxes in the middle, OpenStack APIs and user experience. I mean, that's what OpenStack gives you natively. To run an eBay application, you need to do things like configuration management, metrics, log processing, alerting, monitoring, incident resolution, chargeback. How do you do upgrades? You know, so there is so much more than OpenStack than it takes to run, you know, a business at our scale with the number of developers we have. And the complexity is just amazing. So while OpenStack helped us, it just wasn't anywhere close to solving the complexity at the developer level that we needed to. So we really needed a platform solution where we can abstract out a bunch of this stuff from the developer, right? And that's where Kubernetes came in. So I think that's where, although we were doing really well on the infrastructure automation side, on the platform automation side, we still had a ways to go. And Ashwin's now going to talk about, so this is where we talk about Kubernetes and our journey into Kubernetes. I'm going to let Ashwin talk about Kubernetes specifically, and then he's going to go into the networking challenges that we are having running Kubernetes at scale at eBay.
Thank you, Suneet. So this slide is actually like exactly like how we want the transition to happen at eBay. So right now, if you look at our OpenStack cloud and an application developer who is using it, they go through this four squares there, which is like you start provisioning your application, then you deploy software into that, you constantly monitor, and then you remediate like as things break. So this is like what is expected out of each application teams at eBay if you are a pure DevOps model. And clearly, like from our 2 years of experience, like we have seen that is just not happening. Application developers are not tuned to do these kind of things at scale. So we needed something which allows users to declare their intent and have a system which takes care of that, including all the details which Suneet mentioned earlier. Like it's not just like provisioning a few computes and get the networking alone, but the whole thing which goes along with that. So that is where we saw a really good potential fit with Kubernetes, and we started looking at it early, and we started seeing like what needs to be done to make Kubernetes run on our platform, which is like OpenStack. So what I'm going to talk about is like really quickly like some of the aspects which we have done specifically to the networking side of things, and maybe like a little bit in security. So I may be not able to like go into the lot of details, like but I think you can catch me up after this and we can discuss. Can we go a slide back, please?
Could we go back a slide?
So there are two networking, like a bunch of networking challenges. Like part of it is like caused by our own implementation inside. So our OpenStack has two distinct models like of networking. So the first one is like the overlay-based SDN, which is what, as Suneet mentioned, we use NSX behind the scenes, but using an OpenStack as a layer which developers are exposed to. it is like awesome, it's very flexible, but we have like lots of these scalability challenges like which we have faced over the years on that. But that is like a model. In some of our zones, like, run that. And then we have a larger set of what we call bridge mode, flat underlay, like, spine and leaf architecture, different names, but it's basically a simple layer 3 routed design. That scales pretty well. Like we know, like we've been running eBay on it for a while. But like there's like a lot of automation complexity which we have to use that layer as it is. So then the model, there's like an aspirational goal for us is that everything which we do needs to have an IP which can be routed to. So that adds some complexity because the IPv4 space is scarce, like even internally. So we had to deal with that. Then we have Kubernetes is like a spec-based system which allows you to declare semantics for your global routing, load balancing, and stuff like that. And we need to have implementations because Kube does not always solve the issues. It's a spec more than anything else. So if there's a good implementation in Google Cloud, but for others like who are running private cloud, OpenStack, we need to implement those things. So my group's responsibility is to like, figuring out what is the right modes for implementation of those specs. So I mentioned like the overlay-based model. So this is roughly how it looks like. So we have the neutron layer, which we have from our OpenStack. So the default Kubernetes model assumes that you have some kind of overlays which are running inside the Kubernetes layer. So it's the solutions like Flannel and Calico, Flannel and other few overlay solutions. But like we looked at the ecosystem and said, like, why do we have to reinvent the wheel? We already have an OpenStack-based NSX solution working. So we wrote like our own custom network plugin, and with the help of like the underlay the cloud provided overlays, we have a bridge solution. So basically, like we fork Kubernetes and we write our network plugin, and this knows about the architecture of the OpenStack networks, and it can actually bridge into that virtual layer 2 which NSX offers, and then we manage IPs separately from NSX and route traffic to that. So we can, since we also like do the whole thing over an OES bridge, we have full control over like who can talk to, like which parts can talk to which other ones, and whatever we need to do with that. I'll talk a little bit in detail about after this. So the second model is a bridge mode, which is like where we are putting all our efforts on the production side. Because the first one, as I said, is flexible and easy. This one is like kind of hard. Here, like it's a spine and leaf architecture. You have like a bunch of like racks, and then you have containers which are running on the host, like which are connected to these stores. Obviously, like Kube has a lot of requirements surrounding like how IPs have to be. Each pod has to have its own IP. So there's like a lot of issues which you have to deal with. But otherwise, like this model is pretty simple. We have a provisioner which provisions the routes on all the TARs which are in our systems. So it's a declarative system. So you basically like declare to the system like how many network scopes you need, and that is an input to the orchestration. It's not an orchestration, it's a spec-based controller, just like Kubernetes control itself. It actually realizes this on our TARs. So that is how we have solved the bridging. Again, the plugin architecture we have helps here. We have like our own, there's a few things we had to do to make it work. Like I'll talk about it in the next slide. This is like a problem which I was alluding to earlier. So Kubernetes model says that every pod has to have an IP, and if we have this rough computation on every core needs to have an IP. So assuming that like one of our nodes, like which is a standard size, has a 64 core machine, then we need 64 IPs per node, and we have like about 50 machines per rack, per half rack, under like each TAR's scope. So that means like we have a /20 requirement per TAR if you have to just strictly follow the Kubernetes an IP requirement. This adds up. I think this is a lot of IPs to have, and it's not enough IP for us. So what we needed was a way to decouple IPs from the host. So our solution was to like invent a new construct into the Kubernetes plane to have what is called a network scope internally. So when we provision like a Kubernetes node, we associate it to a network scope. All these things are like done declaratively, But what happens is like there's an IPAM, which we also built along with that, which understands the topology, and it will pre-allocate the IPs as the pods are getting scheduled. So just like Kubernetes schedules like pods, it also, this IPAM picks up like the pods which are scheduled and allocates IPs based on that, based on all the conditions which you have set for that. And again, our network plugin deals with the allocated IPs and does the thing. We also had to do like some amount of like rproxying and stuff like that, so we can convert a layer 2 domain model to almost like a pseudo /32 routed design. So that is how our production networking is working now. So now we can jump into the security aspect of it. So there are two things which we have to solve. Like one was the segmentation options. Like when we have clusters, like how are they segmented? And then when you talk about the application, what about like the access granularity? So you need some kind of like an IAM so that applications which are running on Kubernetes can control like who can talk to them or who they can talk to. And also at the same time, we wanted to give like our operators like a full control over like what is happening like in the system. So this first solution like, was to have zoning done like that. So where you have physical segments either done through like an overlay solution or like physically segmented using firewalls, and then you would have Kubernetes clusters which are per zones. So in production, we have like a bunch of clusters. Like in dev, we have another set of clusters, and you have other secure regions. So these are the full control plane is within the zone. So there's no need to have inter-zone communications. Whenever they do happen, they go through a policy. So so this works pretty well for us. So then we get into this thing of like micro-segmentation, which is like I have applications which are running inside that, and they need to talk to another application. How do you tell Kubernetes to do that? We can write another network plugin and then make it happen. So that's one approach. Like you could call that, or like you could say that tell an SDN in the situation that this is like who you need to connect to, and these are the ports which have to be open, and then only like allow traffic to that. Or the other approach is like you teach application about security. Like so that is like the approach we are taking. What that roughly means is like instead of punting like all the responsibilities of security into network layers or like underneath layers like in infrastructure, a large percentage of that can be handled at the application layer. So what we need is like definitely like an idea of having these policies defined by the application and by the security folks. So the way we are doing that is like by creating a solution which allows you to declare policies. Each application developer, when they spins up their application, declares like who they are allowed to talk to. Now that is just a policy, just like anything else. The implementation can be anything. So for the first implementation which we did was like to use IP tables, like to restrict access between the applications where these policies are applied to. But right now, like the other approaches we are considering are moving the whole thing into the application space. And the models like Kubernetes makes it super simple, because in Kubernetes you have containers all packaged into a single pod. So you could have many pods, many containers running within a pod, and each we could if I assume that there is a pod which terminates all your connection and then uses a localhost based routing to your actual application, you can implement a lot of these policies in the application space itself and leave the network to be like just flat network. This actually helps us even in migrating to different cloud providers and other vendors, like without necessarily having to change any semantics tied to the application. So that is a model which we are like actively considering. So this is like teaching application security by writing policies against that. Obviously, like the network operators and the security groups have to be involved. So we have to like have this audits and all the violations reported, centralized dashboard, ability to revoke certificates, like if you are moving into new like an application space, a lot of those things. So we are working on that front. The other part, like teaching SDN application security needs. So we just saw like NSX has like this cool feature where they can look at the labels from the Kubernetes pods and automatically translate that into infrastructure policies. So I don't have to like specifically do anything. You just like deploy some Kubernetes pods. Applications do that all the time. They just have to label which zone they belong to, who they want to, and then segmentations happen automatically. So those are like two different ways like we want to deal with security. So actually that I would like to conclude there, but I think like if you want to look at where we are now, Kubernetes seems to be like the right platform for what we want to do. It is pretty flexible. It offers like a very easy API server and a spec, which is pretty common industry-wise. And we can add additional policy languages and models to that. And we have done that over a variety of use cases. All our systems to provision these clusters are all declarative. We use the same kube API server. We declare our intent of creating a cluster, and depending on the controller who is behind the scenes, we'll create the clusters in Openstack, and we can write another controller to create a cluster in, let's say, Amazon or anywhere we want, any Google Cloud or anything.
Yeah.
So,
and for those who are interested, we have about 7 or 8 production clusters right now at eBay, and a big part of our focus has been on the operability and how do you deploy these clusters in a fully automated manner, how do you run them. That's actually a lot of heavy lifting that we are doing right now internally, operationalizing Kubernetes on top of OpenStack within eBay. And that's what this year's really been about for us, rather than getting to run applications.
Yep, thank you.
Very cool. Thank you.
Thank you. All right, if you read through the abstract here of the next talk, you may be confused why it's part of this section. And the simple reason is we got the wrong abstract in the program, actually. What you're going to hear about is about how Kubernetes is doing networking. And I'd like to welcome Subbaiah Venkata from Google on stage.
Thank you, Guido, and thank you, Bruce. My name is Subbaiah. I'm a director at Google Cloud Networking. I've been working in SDN since the early days of SDN 2009, when we first met Nick and Martin. They used to come to Google to pitch to Urs and the executive committee. It was very fantastic to actually meet those clear thought process about SDN. We bought into it. Then we executed like fantastic first SDN controller, B4 network, and we published a paper on that. So I'm going to share that. But when Bruce asked me to actually give a talk in Kubernetes deep dive, I thought like, how can I give a Kubernetes deep dive in 20 minutes? And then it's already there in YouTube. So actually I thought like change the subject a little bit more technical. So bear with me, I'm going to present like some abstractions that are missing, the challenges of containers, and then I'm going to talk about what are the problems. There could be some kind of startups you can build based on the problems I'm facing, or we are facing in a community. So let's get started. Thanks, Bruce, and by the way, to Guido to put together a fantastic conference in this. So Facebook like had a at-scale conference sometime back. Google had conferences. We need more of these conferences. Thank you very much. And then CJ is our Kubernetes expert here. So after that, like if you have any more Kubernetes specific questions in compute size, please reach out to CJ. So this is the overall Google timeline, if you look at it. This is the only slide, by the way, I'm going to talk about Google and Kubernetes. So bear with me for a like marketing pitch. The rest of the slides are not marketing pitch, okay? So just to give perspective, Google networking, we have built since like almost a decade, global cache and public DNS, you can do 8.8.8, and we have cluster level SDN networks on watchtowers, Firehose, and B4. After that, we had paper on SIGCOMM on bandwidth enforcement, how to enforce bandwidth on the WAN networks. After that, in 2013, we published a paper in Andromeda, which is almost like at the same time as Nisira is working on it. And we actually delivered, because we were working on SDN for the WAN, and switched our gears to work on the cloud and the Andromeda side, we came to almost the same timeline. But many people doesn't know that actually before Kubernetes, there was containers, and Google was actually doing containers that's called C groups. If you look at the Wikipedia of C groups, you can see that actually IBM, Google, and a lot of people are contributing to that. But Docker, we should give credit to that, as Docker actually commercialized the product as a containers. And then other than the networking, we are doing protocols like open source protocols like Quick and gRPC 1.0's GA last week. You can try gRPC. It's picking up very well in the community. With that, I want to go talk about what is the scope of this. So scope of this is talk a little bit of technical terms and common networking abstractions. After listening to the Nick's talk yesterday, such a clear thought. Bear with me, like most of the things I agree, but maybe he knows already, but I wanted to actually go back to the next question and relate to the containers networking in a minute. Yes, we do have problem about like abstractions in networking. The problem is not about programmability or a lot of compilers or the languages. The problem started in 1970s. Actually, if you look at the virtual memory paper written by Peter Jennings, it was done in 1970s. Virtual memory, virtual networking concept came in 2010s. After that, Microsoft, Linux, and all this came because the abstraction concept existed before the operating systems were there. Then the convergence happened. Because of the convergence of the operating systems, there are only two convergences right now. You go to commercial Windows or Linux. Those are the two things. So any of the innovations in languages, let's say, happen after that. That means networking needs a converged operating system before we have languages or programming or compilers or any kind of things. But sad fact, we are trying to retrofit that. We don't have a ubiquitous operating systems that everybody follows. If we had the concept in 70s that whoever wrote TCP/IP that we need to have an abstract concept called a node or an endpoint and all of this concept already synced into our mind, and all the networking player would have actually created operating systems, then the innovation would have been completely different. So we're trying to retrofit all of that 30 years painfully into the next generation. And it's a painful thing we are going on. Still, we don't have a common networking operating system. It's hard, it's challenging, I like it. Going to the applications, this is pretty fundamental. That when Google talks to a lot of customers, what they say is, yeah, we wanted a lot of networking functions. Load balancers, firewalls, I would say VPNs to talk to them, BGP to talk to different premises, so many things. Second thing, I need performance. We needed X microseconds of latency with, if I give 40 gig link, I'm going to pick the 40 gig link max. If I give 100 gig link, I'm going to do that. That means what's happening there is in the industry is networking is always in reactive mode. It's always applications, compute, and storage driving us. And we are always in the catch-up game, but that means we need to support different kinds of mixed workloads. No matter what, we'll be aware bare metals, virtual machines, containers, running in the same virtual network, we need to interoperate with all of these. That you will see, same thing is happening in container networking. Whatever happened in regular networking, physical networking before, same thing is happening in this thing. So many flavors. If I go to YouTube and trying to figure it out, I cannot really follow this. It's difficult, very hard to actually follow what are these pieces put together to create a stack. What it means to networking is, this is the slide, basically the takeaway slide from this particular talk. Hybrid workload deployments is the future, at least for next 10 to 20 years. There's no question about it. We will have customers deploying in VMs, containers, because I have never seen any network appliance running in containers yet. Network appliances are moving to virtual machines because they need multiple NICs. Each NIC has to have an isolation there. So we will see the VMs, bare metals, everything existing, and definitely we'll see hybrid clouds. I don't think everybody's going to have one public cloud. You're going to see multiple public clouds. Same thing with, there is some services you from in-house public cloud, some service you get from the third party because of the business models. So what that means is abstraction, we should get it right. Need a consistent network model and APIs for all network functions in all deployment scenarios. It's not just network functions, but like nested, double nested, and going to get into deep into what a double nested means in hybrid clouds. We need to think through a lot and come up with like nice 1970s paper kind of an equivalent of abstractions for this model. The implementation wise also, it's better to just the way Linux has done it, you need to implement it very solidly, saying that, okay, if I do on functionality 1, load balancer functionality 1, it's going to work across all the board. across all different deployment scenarios. I don't need to replicate my load balancer for containers differently and virtual machine differently, and then say bare metal differently. So what it means by mixed workloads, let's go like what I mean by that, just a graphical representation of it. One is you have a virtual machine running in bare metal. It's a typical deployment. The second one is you have a containers running in bare metal. That's what the eBay has done, previous talk. Then most of the public clouds are going double nested. You have virtual machines and you have containers running inside virtual machines. The reason is for security reasons. I don't think the containers having a single reusing the operating system of the host machine is secure for the public cloud provider to say, okay, go and deploy the bare metal directly. That means we have a double nesting problem there. So just keep it in mind, this slide, and then I'll be using this slide going forward. So what this means to the public cloud provider, because you have some customer, single customer, using virtual machines and containers and virtual machines, double nested, and we have third party. Third party could be, let's say, Citrix, F5, AV Networks, any kind of these load balancers and appliances there. All of these to interoperate through a single API abstraction, which is very hard. That's what actually eBay is trying to almost retrofit themselves in the last talk to do all of these things themselves. So there's already fragmentation happening in the industry. And we thought about it, let's say, why don't we do one-on-one nested? Why don't we just run one pod, Kubernetes pod, or one Docker container per virtual machine? Because now it comes back, say, the compute guys are actually forcing us in a different direction, because the virtual machines are not ready to be thinned down to support just like one container. That means virtual machines are heavyweight. You cannot have, there's already some kind of applications or some kind of proxies there inside virtual machines that amortizes the cost of running 100 containers. If you run one container, you don't get the economic of scale. The other problem is also like virtual machines a little bit of head start because of all the compliance reasons, security reasons. It's easy to get a virtual machine image that is well vetted and then deployed once, and then you can bring in and run all the containers there. So now comes to how to support like one-to-many nested challenges. So all these slides are about like what are the challenges we are going to face. It's not yet started, but in a year down the line, 2 years down the line, we come back and talk about it. Wow, the entire industry of networking, container networking is so much fragmented, it's very hard to solve. I'll just talk about 4 problems, like for example, the basic problems like IP addressing, routing with the basic connectivity, security like firewalls, and then load balancing a little bit, the 4 slides. And then there is problems that will persist about like access controls, IAM policies, and so many things we don't have time to discuss about everything else. Now, let's talk about IP addressing options. So overlay addressing, there are 2 kinds we can do addressing. One is an overlay addressing or a flat addressing. Most of the industry is actually split. The RFC 1918 has written sometime about like 10 years ago or so by Yakov. Already we are facing a pinch. Some of the concepts that the early networking, we are actually finding it difficult right now. I'll talk about 2 such things. One is IP aliasing a secondary IP addresses. We never use secondary IP address in the physical machines, but the containers is pushing us to use hundreds and maybe 200 such addressing per physical machine. Similarly, we have this the issue of this IP addressing pertaining to us about like if you go deep and deep nested, whenever we go and talk to these high-level application folks, they don't even understand the on-the-wire format. The community is much bigger than us. If I go to Google search and say, I want to write a Google Brain application, they don't even know the socket exists, socket call exists. All they know is I write an IPC or some gRPC protobuf, shove it into the RPC, other side will show up in the distributed system. But all the complexities of all these headers we are adding is creating MTU issues and all kinds of fragmentation issues and difficult to support like mixed workloads. So I don't want to go over all the problems you can see. The security-wise anti-spoofing is difficult because these containers are sending on the wire by different addressing. I can't do a security properly because I need to open up the firewall to say, hey, because it can assume the containers can assume any IP address inside, but on the wire, I need to remove the anti-spoofing checks because we don't know container has moved from one machine to another machine. Now it assumed different address. What about the flat addressing? Flat addressing is good. Flat addressing is actually good, but the problem with the flat addressing is you have both virtual machines and both layers you're sharing the same addressing space. But we never dealt with this before because address management concept was not there before. Now suddenly there is an ecosystem of IPAM, IP address management just popped up. It's called Docker CNI, Docker CNM. So many things are, everybody's facing the same problem about, I need to manage my RFC 1918 space more intelligently right now. If I think that I need 100 containers per virtual machine, I can't pre-reserve. If I pre-reserve that, because there's a lot of fragmentation happens, a lot of IP addresses get wasted. So how can I actually not waste those addresses? It's a hard problem. We need to come up with a nice addressing allocation scheme, or maybe go back to IETF and think about like, at least fix with IPv6 addresses going forward. If I do flat addressing, the challenges are, as I said, the concepts like IP aliasing, secondary IP addresses in the networking industry is coming back. Now each machine should have 100 or 200 IP/32 addresses. That means the routing tables of the underlying network is completely increased by 100x fold. And then the nested writing challenges actually I went through. The problem with the nested one, the routing wise, is somehow the control planes of SDN also is, there's a physical SDN layer, there is an overlay SDN layer, there's a container cluster like Kubernetes masters or whatever the Mesos masters are there. So in all these different layers, you have networking layer stack is actually polluted all the IP addressing and routing functionality there. But as I said, we are seeing all these MTU issues and everything there in networking, trying to retrofit the application's needs. Not only the MTU issues, how can you do in going forward? Now the question is not today, but 2 years from now, how do you do SRIOV from a container all the way to the NIC? SRIOV right now is just works from a VM to a NIC, but if you do a multi-tenant containers inside a VM, how would you do that? And all the grouping mechanism, quas markings, DSCP, hashing problems, it's very hard to solve. And coming to the firewall is a different problem, but this is going to actually create more problems because Kubernetes doesn't support multi-tenancy yet. There is a reason for it. We purposefully didn't support it, but we can easily support it going forward. The reason is this. It will create, if you think about it, it will create 5 levels of inception. If we support like containers inside of VMs and multi-tenancy, and each multi-tenancy you can have micro-segmentation there. That means a particular red container in one can be micro-segmented into a particular application there. That means an application running in the red container is part of a tenant 1, which is running in a VM 1, which is running in a host 1, which is in a network. So it's too much of the compute and the storage are not understanding, but we are trying to retrofit all the use cases too fast for them, which is hard going forward. And the load balancing challenges are actually even deep. For example, the load balancing actually we have solved pretty well in the physical network case, the box case, and VMs case, because getting the VMs utilization or getting the auto scaling of the virtual machines is solved, because if a virtual machine is running, you can collect the utilization of a particular VM very well. you'll run some kind of a proxy there with a CPU, memory, and then you can get it to a control plane, SDN control plane, and then you can feed it to some kind of a nice controller. It's going to auto-scale, or it's going to load balance properly based on weighted load balancing of the virtual machines or physical machines. But if you're running to the containers, the latency and throughput will be dropped because now the container proxy that is running inside the VM is actually doing some kind of a forwarding there. And it's doing a lot of heavy lifting of containers utilization collection. All of these things we cannot easily remove. So we can think about how we can neatly solve this by removing the container proxy. The goal should be a packet should hit directly to the wire and go to the container without any kind of software proxies in the middle. That should be our goal. That said, just want to conclude. Just gave like 4 IP addressing, firewalls, routing, and load balancing as just 4 key areas, but their problems exist on-premise VPN. How do you connect IPsec VPNs on-premises from containers all the way there? Third-party application supporting, there are many problems to be solved there. But no matter what, the industry is pretty young, the container networking. So the future is hybrid. So we need to come up with nice abstractions, and let's converge on a solution. With that, give back to Guido. I have 30 seconds left. Thank you, Guido.
That's a fantastic talk. Thank you very much.
Thank you.
Super. So we've heard 2 talks from the Kubernetes crowd, and we'll now switch over to Docker. So Madhu Venugopal joined Docker through the acquisition of SocketPlane, and we'll now hear how Docker tackles networking.
Let's do that. Hello, everyone. There you go. As Subbaiah said, originally I accepted for a deep dive talk on Docker networking. 20 minutes is never going to be enough. So I changed it to be a design philosophy. It's not going to be a philosophy talk like what Subbaiah did now. It's like exploring the vision of the entire networking world, like to make sure hybrid networking is going to work. But it's going to be mostly about Docker networking and what is the philosophy in which we designed what we designed, right? And what we're designing at this point. Right. So if you look at Docker's mission, it's been like repeated multiple times in many of the forums. It's build, ship, and run. It's about any application should be able to run anywhere, laptop, data centers, cloud, doesn't matter, right? And when Docker came to the scenes like 3 years back, or 3.5 years back, it's an awesome achievement, like from a community, and the community formed around it. We all loved it, right? And then Docker just exploded. It's great. It was working for a single container in a single host. And we were trying to solve the problem of networking at the time by using like natting and put mapping kind of stuff so that everyone is happy, like developers are happy, things just work. So things were happening that fashion. Networking was not even a piece of Docker at the time, right? So as you know, it exploded in the scenes, and orchestration becoming the most important ones where application is not just one container, it's a distributed applications where containers will not be running in a single host anymore. Application must be running in a cluster of nodes, whether it's in a single laptop, whether it's in a cloud or data center. So the networking problems for Docker started coming up at that time, right? So then at the right time where we started a company called SocketPlane, we're trying to solve the exact same problem. So we got acquired. And then our mission for Docker networking was this one. We should do the same thing for networking what Docker did for compute, right? It's a mission that we had. So we started working on that, of course, right? And as Subbaiah said, it's not easy, right? Especially because when Docker came to the market, the solution was right there, so everybody flocked around that. Then opinion starts coming in, right? I mean, of course, we all have a lot of opinions. We're all great engineers, of course, and we all have existing solutions in our hand. So all of us will try to, how do we retrofit my solution into this massive infrastructure that we have right now, right? All right, now, it's great to have a mission statement like this, right? But once you have a community forming around it, once you have opinions on how the architecture should be done, it's going to be extremely hard to get this mission statement right? So I'll come to this one on why it is hard, what is the mistake that we are doing by retrofitting our existing solutions into a new architecture. I'll cover about that. But before that, let's talk about design goals of what we have at this point, right? The Docker is about, hey, write a container, package your application, have all the dependencies in. So once you have an image, push the image to the hub or your local registry. You download it anywhere, it's going to work exactly the same way. Which is awesome. That's exactly what portability is, right? The application is completely in place so that no dependency hell, everything is going to work right for you. The same thing is not true for distributed applications earlier, because once you have distributed applications, the guarantee should be there. Somebody should give you the guarantee that, hey, I have few containers running across my data center. How do they communicate and achieve the exact same thing it achieved in my laptop, local laptop, right? So one of the design goals that we have is, regardless of whether it is a single application running on a laptop or a cloud, it should have seamless portability. That's one of the fundamental requirement and design goals that we have. And users come first. This is one of the most important things that we drive. Users always come first. Everything else comes next. Users are, for Docker at least, users are application developers who doesn't know anything about networking. For them, IP addresses and port numbers, they are all like necessary evil, and they don't even care about it, right? Sorry about that. All they care about is service discovery and load balancing. All they know is, hey, I have a name called a DB. I want to talk to the DB. I don't care how the DB is there, whether DB is in my anywhere, it doesn't matter. It should just work, right? And load balancing, they know load balancing, right? At a different level where, hey, I will be able to scale my service. I have a service called front end. I want to make sure it doesn't go down ever. So I'm going to have like 10 web instances running in my cloud and should be up and running all the time. They don't care about how the load balancing is done. They don't care about how IP addresses are managed. They don't care about overlay. They don't care about any of those. Those are application developers, right? So design goal is to make sure Docker fits their requirements. At the same time, we all know we cannot take an application to production without getting the blessings of network operators. So we need to make sure network operators also understand the design goals and try to fit that. So many times, the problem that I face when I come to talk to people with a lot of experience in operations, they say Docker networking is too simple, right? So they cannot digest the fact it's too simple. It's a hard problem for me to explain. Yeah, it's simple in a command line, but if you look under the hood, it's awesome, right? But the next problem stands that, all right, let me open the thing under the hood, let me show what is inside. Now I'll talk about net filter rules, I'll talk about IPVS. Network operators scratch their head. They say, what is IPVS? Why are you talking to me about namespaces? I don't know anything about Linux networking. Are you going to make me read about Linux networking now, right? That's the next problem challenge that we face. But the problem here is, applications are running in the host, right? Operators, please realize that. It's not running on a router, it is running on the host. Now, when the application is running on the host and application developers require a guarantee from the platform, and the first important thing is to make it simple, right? That's another thing that I have where we have been used to selling complexity, right? Especially in the networking world where we sell complexity. We don't sell products anymore, at least before the SDN world. We just started selling complexity. We just started getting certificates, and we corrupted the network operator's mind by showing a lot of CLI knobs and stuff like that. So once you make it simple, people cannot digest that, right? So anyways, stopping my gun on that. So the users are application developers and operators. So we face a challenge at this point where application developers are able to understand what we are trying to achieve, but operators, they find it very hard. When it is simple to configure, they find it very, very hard. So we as a goal that we have, we are trying to explain, we're trying to educate people on why it is simple, how it can be simple, but even more powerful, actually. And to satisfy many of such requirements where we are making pluggable stack now, we have batteries included. We have zoned down on VXLAN as our basic overlay networking for multi-host networking, but it's swappable. So essentially, we made it swappable to make sure we address various requirements that operators have. Two requirements where some applications cannot handle overlays, right? Some of them requires MAC VLAN. They want like high-speed connectivity. They can't have latencies and stuff like that. So we have MAC VLANs and IP VLANs, so on and so forth. So we made it swappable by, it can be a plugin by any vendor, but also it can be an available drivers in Linux itself, right? So these are the design goals that we have. And this is where the problem starts for us, where these design goals may not meet with the community's, the vendors' interests. So this is where the friction starts, and this is where all the concerns with the networking and why we don't. We see a lot of icons there in the previous logos in the previous slide is because of that, actually. Okay, so I want to talk about this quickly, and then we'll go to the bit more interesting stuff. The abstraction, as we talk about, right? I'm glad we, even Subbaiah spoke about abstractions, but I will talk from my perspective, from my own experience on how I saw abstractions myself and how it's evolving now. These are the days where, like, when I started my career, the networking was driven by standards, right? Where IETF, people, it was exciting for me. Personally, I stumbled in networking accidentally, but it was exciting for the first 2 years. I learned a lot, of course, but after 2 years, it's just a plateau. I just didn't learn anything. For next 10 years, it's been like it's a sad state of affairs, right? I just keep doing a CLA jockey. I was doing a lot of stuff which I was not proud of at all. But then came 2011. I still remember Scott Schenker's talk and Martin's talk. That's where the new abstraction that it hit us, called SDN, right? This actually changed everything for me and most of here, I believe, right? All of us started challenging the status quo of networking need not be this hard, need not be driven by somebody smoking cigars inside a room, right? It can be by us, by developers, right? To actually have a better abstraction and make things work really well. So if not for anything, I'm not going to talk about open flow or anything. If not for anything, SDN challenged the status quo, and the new abstraction was born, right? And just imagine this one. It's been just 5 years. So the industry has revolutionized at this point, completely, right? And hence, we can have more abstractions on top now. So people are talking about policy-based networking. There are lots of talks about microsegmentations and so many things, right? It's all because of just simple that software-defined networking, right? As a challenging status quo. Then comes Docker networking, right? So I didn't purposely say container networking there. I meant Docker networking because the industry is still not mature yet, right? So we are still innovating on this one. Lots of innovation happening at this point. So Docker, we have our own principles. As you saw, we have a mission of making networking portable, seamless across the platforms, and it should work just like what compute did. The Docker compute, the way it did, networking should work exactly the same way. So a lot of challenges to face. I mean, we're facing at this point to make sure the community understands where we are, what the abstraction level that we are getting into. So innovation is always a chaos, so we'll get there. Okay, so this is the slide. This is about the networking model we have. It's called the CNM, right? There's a lot of discussion about CNM, CNI, so on and so forth. This slide is a bit messed up, but it's fine. So the networking model is one of the abstractions that we have. It's a simple abstraction that we have. It's our network, endpoint, and sandbox. And of course, we have drivers and plugins. So to me, what abstraction provides, what is the, why we need abstractions, right? Is that any high-level architecture, any applications or users should get a guarantee, right? The abstraction should provide a guarantee so that anything that's built on top of it should assume that things are taken care of without they have to do reinventing stuff. So for us, when we say network, what we really mean here is network is an object which guarantees connectivity between endpoints. As simple as that, right? So whoever is going to use a Docker network, they are guaranteed that any endpoint connected to this network will have reachability. Whether the network is over overlay, whether it is using MAC VLAN, it doesn't matter, right? All they care about is network, and connectivity is guaranteed. An endpoint is an interface. And if you look at a laptop, we have an Ethernet jack. Think about it as an endpoint, as simple as that. So if you have an endpoint, that means you have an interface for you to talk to. A sandbox is In simple terms, sandbox is a namespace. But we don't call it a namespace because namespace is a pure Linux terminology, while there are other platforms which doesn't call it namespace, so we just call it sandbox. So sandbox is a namespace, and we don't even call it a container because sandbox can be used for containers or non-containers. That's why we design it now. So with these three basic abstractions, we're able to achieve so many things, which I'm going to talk about in the next slides about the features that we added. And if you look at the last one, the drivers and plugins, they are actually what is driving the entire networking to work. This abstraction is purely for the high-level systems to make use of Docker networking, but what actually makes things work are the drivers. So the same abstraction is exposed to the applications or the users of top of networking, orchestration entities for that matter. The same abstraction is being used by the drivers as well. So this is where the community actually comes in. We had so much discussions on why Docker doesn't provide the namespace access to the plugins, right? This is for developers who work with the Docker ecosystem. They understand this, where every container has a namespace, and also there's a namespace on the host namespace, right, for the plugins to manage. So Docker actually manages the container namespace, while the host namespace is managed by the plugins. So what the CNM guarantees is that the containers, the namespace is completely managed only by Docker platform, so that it can guarantee multiple interfaces to be attached to the container. It can have new features without impacting the existing plugins. So that's why the abstractions are important, where guarantees are given, and we will be honoring the guarantees. If, for example, if we provide the namespace to the plugins or drivers, container namespace, then the platform cannot guarantee any such abstraction guarantees that we provided, right? So this is why the abstractions are important. Guarantees are very important for the higher level layer to actually make use of the networking layer. Right. So I was surprised that nobody actually congratulated Linux for this one. It's 25 years of Linux now. It's amazing, and all of us here, I think, we're touched by Linux in this case, especially Docker, right? Docker, we just make use of Linux like anything, right? So it's the only thing Docker is built upon is based on Linux now, and of course we are working on Microsoft as well. But the building block of Docker is C groups, namespaces, and drivers at this point. Similarly, if you look at Docker networking, it uses network namespace, net filters, IP route 2, IPVS, and all the network drivers that is available there. Bridge driver, VXLAN driver, MAC VLAN driver, and IP VLAN driver, right? So if you install Docker today, it make use of all the Linux goodness right there, right? And by the way, I love OVS, right? Whenever I get a talk about OVS, I talk about OVS. In fact, we originally used to use the OVX, VXLAN as the way to do it, but what happened is the Docker as a platform want to make it very, very, very simple for folks to just install and start using things. That's why we started using the Linux drivers itself, right? And since they are plugins, so we are using OVS as one of the plugins for doing the VXLAN activity. So I don't have a lot of time, but I'll just quickly cover the features that we have now. So thanks to CNM. So CNM is just an abstraction, right? So with this abstraction, we're able to provide lots of built-in features. Like the VXLAN overlay tunnel is built in. We have encrypted control plane and data plane, where every single entity that is that's being exchanged between the Docker daemon, the control plane, which is based on gossip, is encrypted. We have data plane also being encrypted. We use the IPsec modules of the VXLAN, of the Linux to encrypt the VXLAN data as well. We have load balancing, service discovery, routing mesh, all the features here, right? As you can see here, right, this is a simple slide, of course. The developers actually dig the bottom 3 lines. They understand what is load balancing. They understand what is service discovery. They know what routing mesh is. While the operators dig the top portion, right? So even in slides, I need to make sure I cover both the kind of users actually. So with Docker 1.12, orchestration is built in. So it's called a swarm mode. So we don't have a central control plane anymore. It's a fully distributed control plane thanks to gossip. And we use Raft for exchanging the management configurations essentially. The control plane is, as I said, is gossip based, and we scale really well. Now we don't actually gossip across the entire cluster. We gossip only within the worker nodes where this container is being launched, right? It's a massive scale thing where if you have a massive cluster, say 5,000 nodes, if you start gossiping across all the 5,000 nodes, we're never going to scale. We're never going to converge. But once you have an application scoped gossip, it's going to scale much better. It's going to converge much more faster, right? It's one of the innovations that we added in 1.12. It's pretty cool. And also, the gossip is available for the plugins to make use of. Any plugin can make use of the same Netescope gossip. They're going to scale exactly like what Docker Daemon does today. And of course, we have encrypted data plane. We use IPsec tunnels. It's optional, of course. They could configure with IPsec tunnel, and it's fully encrypted in the cloud or in the laptop. So we have service discovery. Service discovery is built again thanks to CNM, right? It's all possible because of CNM, because since Docker manages the container namespace, we're able to manage the container namespace networking stack as well, so that when an application is running on a container, we actually manage the DNS space as well. So we're able to inject the DNS resolver on all the containers whenever there's a requirement for a service discovery. And since Docker also runs a DNS server internally, we're able to provide this service discovery seamlessly. So all they have to do is just write an application without having to worry about IP addresses or port numbers and whatnot. Just use the names, and things just start working naturally. And we have an embedded load balancer. Again, CNM and IPVS, we're able to, using VIP and service layer, we're able to introduce IPVS-based load balancing right inside Docker itself. And of course, we have routing mesh as well. For us, for network operators, routing mesh might be a new terminology, but routing mesh is nothing but it's an edge load balancing, essentially, where in a container workload, especially in an orchestration system, containers can be scheduled anywhere in the cluster. We don't want, the user need not actually know where the container is running. So the traffic, north-south traffic essentially, can hit any of the worker nodes or the cluster nodes, and we were able to load balance the traffic appropriately and send it to the right container in the right place, right? Again, abstractions, right? Abstractions. It's about CNM. We reuse the same overlay networking. We reuse the same namespace mechanism. It's exactly that. So when we implemented this routing mesh, it's a beautiful thing where once you have abstractions right, it's really beautiful to reuse the same thing and make things work and solve real problems. It's a real problem. If you go to any container workload deployments in any of the cloud, you'll see this is a big problem where everyone is scratching their head on how to do this one, right? We're able to achieve this it's simply using just because of the right abstractions we have. And I'm way over time now. So even though we have so much features that we added, it's all incremental. So Docker, we release it quite often, very regularly. It's once in 2 months. It's sometimes insane. But yeah, we don't add features like in one go. We just added the features in every release. And as you can see here, we built upon the previous features that we added. And the first thing that we spent time to get it right is the CNM. And I hope we got it right. And that helped us move forward to all the cool features that we added. And with that, I am done. Thank you.
Perfect. Thank you. Super. All right, we had Kubernetes, we had Docker. We're now going to complete the trifecta of container technologies. I'd like to welcome on stage Toby Knaup from Mesosphere.
All right. Hi, everybody. So Toby Knaup from Mesosphere. For those of you who don't know us, we're about 3.5-year-old company. And myself and my 2 co-founders, before we did this, we built the infrastructure at Airbnb and at Twitter using a open source technology called Apache Mesos. And so what we did at Mesosphere is we took this open source project and productized it, and that's called DCOS. So we have a bunch of experience running large-scale container deployments. Twitter production has been running on containers using Apache Mesos since about 2010. It's close to 100,000 physical machines today, all running on Mesos with containers. So it's many more containers than that. It's in the millions. And so what I want to talk about is really just, what have we seen? What are the patterns we see and the challenges that people are facing, based on our own experience and based on our customers' experience when you take containers to production, right? So containers offer a great developer experience, but when we take them to production, with any new technology, there's certain challenges. So I want to talk about that and then talk a little bit about how we solve some of these challenges in DCS. All right. So what problems do we need to solve as it relates to networking, right? So we need service discovery and connectivity. Containers are very popular for microservice infrastructure. So you have a lot of services running in your cluster. They can move around. It's a lot of small pieces. You need to make it so those services can find each other and connect to each other. We need service and container security, right? You have a shared infrastructure for containers. You can have many containers running on the same machine, so you need to be able to segment your network and provide security to those applications. And then the third thing is you need to provide application availability and service updates. One thing that containers enable and microservices as well is it allows developers to iterate really fast. At Airbnb, we deploy 10 to 20 times a day to production. So you need to be able to handle this, this rate of upgrades. So containers bring new challenges. These challenges that I just talked about, right? Those are not new. We've solved these problems before, but because of the way containers work, they bring new challenges, and here they are. So first, they bring a huge explosion in the number of endpoints. This is what Twitter's infrastructure used to look like. On the left, they used to call it monorail, so big monolithic code base, talk to a few databases. That was Twitter, around 2008, 2009. And they went to a microservice architecture, which is on the right. They have more than 100 of these services running today. And so you have many more endpoints, many more services, hundreds of services, each of those services consisting of a bunch of containers, lots and lots of endpoints versus a more traditional enterprise infrastructure with a monolithic code base. The next thing that's really challenging is you have constant state churn in your cluster. Many things happening. Developers deploying to production on thousands of machines, one deploy. You have things failing, right? This stuff it's complex infrastructure. Things can fail in complex ways. Sometimes you have an erratic service that sends too much traffic to another service. Like all these things happen, constant state churn, tasks failing, machines failing, all that stuff. And basically everything fails all the time. Famous quote from Werner Vogels, the Amazon CTO. This is also not new for containers, but it's just a good assumption to have in the back of your head. Typically today we build a lot of these infrastructures on off-the-shelf hardware, and so things just fail all the time. So when we design these systems, we just need to keep that in mind. And then this. What if I told you the inmates are running the asylum? So containers really give a lot of power to developers. They can do a lot more things that they weren't able to do before, and they will use that power. So that is a challenge, right? So how do we set the right policies? How do we let developers do what they want to do? And that trend is not going to stop. That's going to continue because empowering developers is a really good thing. Lets people move faster, right? So, but how can we let them move fast and at the same way, keeping things sane? So let's talk about what developers want since they're in charge now. Let's look at their needs. So everybody wants an IP per application instance. When there's been a bunch of different attempts for making networking work for containers and for microservices. For example, bridge mode, where you run containers behind a NAT on a machine. That's not a really great experience. It actually breaks. It has performance impact first of all, and it also breaks some distributed systems. Especially those that advertise to each other on different nodes. Those IPs behind a NAT are not routable, so it breaks some of those applications. So people want an IP per application instance per container. They want to treat containers basically like machines. They should be addressable with an IP from anywhere in the cluster, and they want to use DNS on top of that. So it's really important to people. Some people want to be fast. Containers are mostly used in development right now, so you'll find a lot of solutions out there that work great in development mode and provide a great experience, but they're not very fast. But as more and more folks are moving to using containers in production, they need to be fast, so performance overhead should be minimal. Some people want security, right? It kind of depends on where in the spectrum a customer falls. The more web scale kind of companies, maybe security isn't that important, but then you go into highly regulated industries, so those folks need security. Some people want to run on-premise and on clouds. It's some people today, it's probably going to be everybody tomorrow. That's going to be the new norm. People want to run in a hybrid mode, and they want to be able to run on multiple clouds. Nobody wants to edit application code. We don't want to force people to change what they do. And the last one, nobody wants to talk to the network engineer. Sorry. But we can find good interfaces between developers and network engineers so that a developer can express their intent and a network engineer can still do their job and keep things running. All right. So when we talk about load balancing and service discovery, which is for a developer, that's one of the most important problems to solve in microservice infrastructure. How it used to work is basically this. You had a client hardware load balancer running on a specific machine with a specific IP and port. Load balances to a bunch of servers. We know what the IPs are of those servers. They never move. The applications are always on those same servers, always running on the same port. Everything was fine. It was simple. It was great. When microservices came around, it started looking more like this. This is kind of generation 1 microservice service discovery, simple service discovery. A lot of companies that did microservices early, like Airbnb and Yelp and Netflix, it always kind of looked something like this. You have a client app. It needs to talk to a request proxy. The request proxy knows where things are running, and every application, when it starts up, has a sidecar process running on the same machine that monitors this application, does health checks, and then reports to a central registry where this application is running, right? It's no longer running on a predefined port, because now we're running these microservices, a lot of them on the same machine, so you can't have two things running on port 80. So they run on different ports. We need to monitor that. We need to report that to a registry. We need that service proxy. So it's pretty complicated. Not a great user experience. So if we take all that, right, so we saw the developers' needs. We saw, generation 1 service discovery, not a great user experience. We came up with some design goals and some requirements for what this should look like. So first of all, we must be agnostic to the underlying environment, because hybrid will be the new norm, and pretty much everybody wants to run on a mix of bare metal and cloud, public cloud, private cloud, multiple cloud providers. Needs to be completely agnostic. Should require minimal changes to user code in order to work, right? We cannot force people to adopt a new RPC library, because that means they need to change all of their applications. We should provide similar services to existing environments, right? Things should feel like what people are used to. The load balancer should feel like a hardware load balancer, for example. And people should be able to use DNS. We don't want to require a change in organizational procedures. So if you really put the developers fully in charge and fire all the network engineers, that wouldn't be great. So let's see how we can use our existing procedures and use new APIs and new contracts to run our infrastructure. We want to be secure. Environments are going to be multi-tenant. A lot of things running on the same cluster, on a shared cluster. So we need to do segmentation, need to be secure. And we need to design for massive scale. So like I said, Twitter is about 100,000 physical machines, millions of containers. Even more traditional enterprises, 100,000 containers are not uncommon. That's really the scale that a lot of companies are running at now. So if you take all these requirements, here's what we came up with. Here's how we solved that problem. So we're doing service discovery using virtual IPs. So when you start a service for the first time, you assign, as an operator, you assign a virtual IP to that service. That IP never changes. And the control plane that sits behind that maps that to the actual endpoints. So it appears like a fixed hardware load balancer that we're used to. You get an IP and a port that never changes. We had to build, this is really the core of it, the control plane is the hard part. So like I said in the beginning, it's the constant state churn and the scale that this needs to run at was really the hard part. So we looked at a couple different options. We looked at a bunch of things that are well known in networking, like Dijkstra, and also some of the newer research like High Power View and SWIM. Those are gossip-based failure detection protocols and routing. So we took all that and we took CRDTs, which are known from distributed databases. There's REAC is probably the most well-known that uses these. So conflict-free replicated data types is what they are, so they can handle a lot of state changes without the need for synchronization. And so this is how we were able to handle this constant state churn. It's using IP tables, NFQ, and DNAT. So what it does basically, and I'll go into details, NFQ allows you to process packets in user space, and we exploited that to do the mapping from virtual IP to the actual endpoint. So I just want to talk through an example of how this actually works. So there's a few code names in there. I'll explain those real quick. Lashup is basically the control plane. So it's the thing that disseminates the state changes. It's what keeps the mapping of IPs, of virtual IPs to actual IPs, disseminates the state. Minuteman is basically the agent that runs on every machine that talks to the kernel. And then we have a user app and the actual server here that runs our application on a specific IP and a certain port. So to use this, first thing that happens is a user creates a new virtual IP. They want to start a new service. Let's say it's 1234 port 5000, and it's pointing at one backend in this case. Now, when we have this user application that wants to connect to this virtual IP, it opens the connection, and what we do is we intercept the SYN packet. So we take the SYN packet, and using NFQ, we hand that to Minuteman. Minuteman looks at it and says, OK, it's going to this virtual IP, that port. And then it basically does natting, but on the client machine, not on the destination machine like it works with bridge networking. So, and then it looks up, it does load balancing, right? It picks one of the backends for that virtual IP. And then just goes back to the kernel and programs that flow into the kernel. So instead of going to that virtual IP and port, going to the actual endpoint. And then from then on, it's really just opening, running the connection like it normally would. All that rest of it happens in the kernel, so there's really zero overhead except for the first SYN packet. Now, this solves a lot of problems. We've done service discovery in a way that's not foreign to app developers, where they can use all the things that they're used to. They can use DNS. That's actually a really, really hard challenge. I mean, everybody loves DNS, but as we know, we're handling a lot of different ports here, and serve records are a really cool thing, but unfortunately nobody supports them. So we had to work around that, but by using virtual IPs, we're still able to let people use DNS and let things run on different ports. And by the way, another thing that I didn't talk about here, Minuteman also provides IP per container, so you can actually access your containers from anywhere in the cluster. You don't have to go over NAT to do that. And so, as we saw in one of the previous talks, that brings its challenges too. So you have to be really good at IP address management. You can't just assign a full /24 to every server and a /16 to every rack. You're going to run out of IPs really quickly. So what we did is we made that configurable. So depending on depending on how many containers a user runs on every server, you can configure how big the subnet is that you allocate to every single machine. So it solves that problem, at least to a certain degree. But the challenges remain, right? So cloud networking, unfortunately, is very different between different cloud providers. There's other solutions, other routes we could have gone down to that we weren't able to do because certain things don't work in certain environments. So I'd say this was probably our hardest challenge, is really, you can't make many assumptions around what's supported underneath. Cloud networking also is sometimes buggy. Not all the clouds are as mature as we'd like. So you have to work around that in some cases. And then the last point I think is going to be one of the most important ones, and where we're going to see the most work happening in the future. It's really QoS between services. So what containers and microservice architecture allow, and paired with a cluster manager, what they allow you to do is start a lot of things really quickly and tear down a lot of things really quickly. If you allow your developers to do something like blue-green deployments, which is very popular, all of a sudden you have twice the number of endpoints, right? And so you have twice the number of endpoints talking to your database, generating twice the amount of network traffic. So bringing order to that chaos and giving guarantees to certain applications, because you might have production services, latency-sensitive production services running on the same machine as your big data batch processing systems. So that's one of the big challenges, and that remain, and where I'm really curious how we're going to solve that. There's obviously a lot of primitives available in the kernel that you can use to do QoS, but tying it all together and it's going to be a real big challenge. And it's going to get even harder when in multi-cloud and hybrid deployments, when you have to go over the WAN and things are kind of unpredictable. So that was it. That is my short journey through networking in DCOS. Thank you very much.
I'd like to invite all the speakers up here. So for the Q&A panel, you can join me here. Pick any seat, open seating. All right, so those are some great talks. I think there were some common themes. There was some slight differences, which was interesting to see. But I mean, if one thing is sure, I think we're seeing, are we out of chairs here?
Oh, yeah, okay.
Yep.
The one more.
Okay, then I'll take the other side here. So let's see, any questions from the audience here?
Yeah, I have one.
Please.
You mentioned that cloud networking is sometimes buggy. Can you give us some concrete examples of something you've seen? Just curious to see.
Examples of cloud networking being buggy? We've seen everything. It starts with, sometimes you bring up a machine and the IP that is assigned to it changes during boot. That's an extreme example. Sometimes high packet loss. You have noisy neighbor problem. You have just firewall rules not being applied correctly. It's really the whole range.
Do you have any, just to follow up, any particular the difference between private and public? Do you think that it's the same bugginess level, or?
Same bugginess level between private and public cloud. I'm not sure. I think it probably depends on how people set up their private clouds.
Bruce, over there.
Yeah, so I was intrigued by the contrast between the talks. So if I were to try to paraphrase the last three talks, so I think from Subbaiah's perspective, container networking is a total disaster. It's completely fragmented, and we're all going to die. If I were to paraphrase Madhu and Toby, it was like, we have an awesome solution, but then if I compare those two against each other, well, actually things are fragmented. So it seems like you two guys sort of both feel like networking is in relatively good shape compared to where Subbaiah sees it, but you are also backing up his assertion that it's fragmented. So discuss.
Discuss. I'll go first. It's definitely fragmented, definitely. And to be completely honest, like before we embarked on this journey, we weren't really we didn't really think we'd have to solve a problem there, because there's so many solutions out there. And we looked at the number of them, and what we saw, most of the container networking solutions were really optimized for a great developer experience, which makes sense because at the time, that's what containers were mostly used for. But our challenge was that we work in a lot of very large-scale production environments, and so none of those solutions work there. And that's why we had to go down a path where we optimize for scalability. And so I think it is really fragmented right now. I think we haven't even agreed on what the APIs are yet on top. There's some that look promising, like CNI, but I think right now we're sort of going broad. We're trying a few different approaches, and I hope it's going to converge at some point.
So can I take the question? So let me actually, I'm not saying that this is not going to work. Let's compare that with our traditional Unix culture. So Unix had a nice API, Unix file system APIs, and everything was abstraction for very well defined. There are a lot of Unix flavors for there, FreeBSD, NetBSD, so many BSDs, a lot of differences between them, Linux and Windows, so much fight was going on. It's the same state, except that we don't have abstractions defined. That's what I'm trying to get at it. Every industry goes through a lot of fragmentation early on. Slowly something will die down, something will emerge. My worry is we have no common set of APIs and abstractions defined, like the Unix file system defined it. It stood its working time for almost 30, 40 years. That's my point.
So can I expand on Bruce's question? Is there a difference here depending on whether you ask people that think about the container ecosystem sort of in isolation versus somebody running a complete data center, right? Because I think to your point of hybridity, right? I mean, at least in the enterprise space, a good rule of thumb is that any technology that's ever been invented still runs somewhere in an enterprise data center, right? I mean, you have mainframes and you have AIX systems and bare metal and virtual machines of all flavors, than containers. When you talked about container networking, this was really about networking within a swarm of containers, right?
Yes.
But if for example, eBay is running a data center, they have to think about connecting containers with virtual machines. I'm not sure if you have a mainframe running in some corner.
No,
but,
thankfully.
Probably, right? So yeah, you have, Ali, right? And so are there different levels of networking evolving, right? I mean, do we have sort of the intra-container level networking and then maybe the data center networking, or I'm not sure if David Watt is still here, maybe there's an ACI fabric underneath, so we have an ACI level, overlay network? Are we stacking overlay over overlay over overlay just for different purposes in order to keep control apart? What is?
I think that's what is going on. That's my point. Actually, we are creating overlays. Especially my talk was about like public cloud. We are creating these overlays for making the virtual networks for each customer multi-tenant separate. But that has one dimension. Second dimension, within the same virtual network, customers are asking for different requirements, forcing us to something go for a direct VM with multi-NIC interfaces, some things with container support because of microservices are asking for containers. Someone is saying we need bare metal because of the high performance. So in a single virtual network and a single tenant in a public cloud, all of these workloads are placing place, but each of them are being solved by overlays, some kind of an overlay because of the control and visibility and monitoring or whatever reasons.
So, sorry, go ahead.
Go ahead.
Yeah.
So I have a comment, from a user perspective. I think we live in a pretty confused world right now. It is really very confusing. So, I mean, I think Ashwin talked about this. Within our environment, we have overlay running at a pretty reasonable scale, and we have bridged mode running at a pretty reasonable scale as well, and then you throw containers into the mix. It's actually creating, we are right now actually having to come up with our own models, which I'm really wary of because I don't see any convergence, really a consistent message in the industry about how we're going to solve these problems for containers. So yes, we are doing something because we need to solve the problem, but it's something that we are very wary of. So I think we all need to talk a lot more, especially you guys, to solve this problem and align on it. It is quite very fragmented right now. They don't have a consistent message.
I mean, which is not that surprising that it's confusing, right? We're going through one of the probably biggest
Yes.
structural changes in IT right now, right? And if you were stuck in the middle of the French Revolution, would ask people about politics, you would probably get, a very interesting range of answers, right? And so we have the same thing in IT right now.
Yeah.
So I'm from the, what would that be, the dinosaur age, where VMs were still cool. And so from a container perspective, what's the right way of integrating containers in the rest of the data center? I mean, let's assume for a second we're not 100% containerized yet for a second, right?
I mean, I think if you ask me, like you would start from the applications which need control for the entire life cycle, right? So organizations like eBay, we have the experience pretty optimized for the large percentage of the use case, right? Like for 90% of the use case, we pretty much know what they want. So we have systems which are built out. We can use VM to roll out their applications, pretty much like things work perfectly or near perfectly. There's like the long tail use cases, the 10%, which needs like this control, like, distributed applications, which could, spring up somewhere, needs to talk to each other. So those are the, the cases which, containers are a good fit. So our strategy is to like identify those use cases, go solve for them, and, completely decouple their complexity which they see of infrastructure and start from there.
Yeah, to add to that, I would say that containers need to be a first-class citizen.
Yeah.
The transition from the old way to containers is not just going to snap over. You're not going to one day wake up and have your whole deployment be containerized. So you need some of your services that, maybe your mainframe, whatever, is still running, but you got your front end running in containers, and that's serving everybody great. And those things need to talk to each other on the network as if they're peers, not as if they are operating at a different level, at different levels of overlay. And I think that's why it's so important that we figure out what those abstractions are.
All right.
Question.
Who's talking here? I guess.
I'll do one
perfect,
quickly
like that.
because I'm obligated to, and everyone knows what question I'm going to ask. Madhu. But every single person has talked about scaling problems on addressing. And we have this little protocol called IPv6 that actually would address every single problem that you guys have mentioned about at least the scaling from the address side. And I'm on the California V6 task force, North American V6 task force, so I'll get off my high horse. But there are great designs that I've gone over that I think would be very scalable to solve a lot of the problems structurally here. Why hasn't the community looked more seriously around V6? Certainly the public clouds are part of the problem, and that's being addressed. I think by the end of the year, we'll probably see some pretty interesting things there, but I'm sort of curious what the thoughts were from Docker, from Mesos, and from Kubernetes about what's going on in V6 and why that push hasn't happened.
I can start, right? I don't think it's a question specifically for containers, right? IPv6 has its own challenges, and we all know that. I mean, we have seen IPv6 there for many years now, right? And we're all trying hard to make IPv6 a reality, right? On bare metal VMs, so it really doesn't matter. But containers really explode the need. I can totally see that, right? And there's a lot of work that's being done now. Of course, they're all in various stages, right? And yeah, I'm not even proud that, hey, IPv6 is working great in Docker. It's not, right? So we are calling for help, actually, right? Where folks, please contribute, participate in the open source, right? And help us take the IPv6 to the next level, really, at this point. So that's where we are.
So I would love to solve that problem with IPv6, would love to. And the problem, you gave part of the answer yourself, right? Some of the clouds don't support it. And if you go to private data centers, it's really operational inertia. And so the first time, we actually built a prototype for this that was pure IPv6 based. And we knew there was going to be resistance, but we thought, hey, let's just show people how it works, show the benefits, and then maybe we can overcome that inertia in some of the organizations. Turns out we weren't able to do that, unfortunately. So the answer we got from most customers is IPv6, maybe in 2 years, maybe in 5 years, not even thinking about it. That's really the challenge. There's just a lot of inertia still.
Prashant.
Question here. I wanted to give one context, which was, the way I sometimes think of networking is it's like highways. There are cars running on the highways, and you can replace the cars. You can innovate in cars, but it's very hard to innovate on the network, on the highways. Even though it seems like it's so simple, but when we get to production, serviceable, manageable, scalable, resilient network, it's very, very hard. As the eBay chart showed, the amount of things one needs to do. So my question is, we went through this journey with OpenStack, and many of you been part of that journey in OpenStack networking. It became a major problem and continues to be a thorny issue. What lessons have we learned, and how are we applying that to container networking to actually make it work, day one, hopefully?
Great question.
Ashwin?
I want Madhu to take it.
Me? It's a hard question, right? And I don't want to tell the truth that what I think, right? Because I don't want to hurt folks whom I know in the OpenStack community. It's again abstractions, right? I mean, that's where I'm coming from, actually. So if you look at least Docker as a project, we have a clear focus on users in mind, clearly, right? Users come first, right? So if we have a clear focus, clear mission on what you want to get to, then it's fairly easy to implement stuff towards that. But if you don't even have a focus, right, you just don't know where you're going, right? That's the, I know it's a high-level answer, but you can derive whatever you want to derive from there. Yeah.
So I would say that we need to change the way we look at these things, right? For example, most of these problems are application specific. At least from our experience, we have seen that OpenStack is not at the right level of abstraction. You're still dealing with VMs and stuff like that, and you lose what you're intending to do, which is running an application. It has to be simple, and everything has to be teed off from that step downwards. So I think if there is any learnings to be had from that thing, just putting the developers as the #1 thing and starting to work from there. That is the mistake which I think OpenStack did. Hope containers do not get into that and complicate the world over.
Maybe can I make the question more precise? I mean, if you look at OpenStack, there's two observations. One is the Neutron plugin, right? We had a couple of iterations there. Is there anything we can learn from the plugin mechanism? Was that fundamentally the right approach? Is that the wrong approach? Is there something we should do structurally different? Can I don't know, Kubernetes and Mesosphere and Docker make this vastly better this time? And if yes, how?
I wasn't part of the OpenStack part.
You just claim any responsibility.
Yes, I'm also not part of the OpenStack. I think my belief is yes. I think the plugin model gives a lot of autonomy and a lot of innovation, because a lot of things, but I don't think that will solve the plugin model solves all the problems. So OpenStack is open. That means people should just innovate in a different way. So whatever wins, let's pick that. So customers are the one who's going to pick. So a lot of deployments will happen based on OpenStack. Google is not OpenStack based. So whoever is deploying OpenStack is going to pick some plugin model. Then that way, the organic adoption will happen.
Is the batteries included philosophy? Did that come a little bit out of OpenStack, where I think the batteries that come with the package are fairly weak? Is that a fair statement?
So, okay, again, I'm going back to the same concept, right? Focus is most important, right? Focus on the users, solve users' problem, right? Rather than retrofitting the solutions that we have into a stack like OpenStack. That's a big problem. It's a huge problem, right? That's why I'm trying to be nice by saying that, right? So once, as a community, if you focus on the user's problem and trying to address those problems, that's the good learning I had personally, right? Instead of just, hey, you know what, I have a great solution. Let me see how to plug this into the Neutron APIs, right? That is a disaster.
Yeah, I think to add to what Madhu was saying, and to maybe extend your metaphor, if a developer comes and says they want to drive their car down your road, now with what Docker's doing with CNM and what CNI also does, you might need to tell them what kind of tires they're going to need to do. And you might need to be very explicit about, here are the tires you need to drive down my road. Because they don't care. They just want to drive their car.
Yeah, sorry,
so,
Dave.
And I apologize, I had to step out and missed one of the talks. So this might have been covered, but it seemed to me in most of your presentations, security was up there as a requirement. And then I didn't really hear anything about what you were doing about security or isolation. And if you think that the devs don't want to speak to the network engineers, they really don't want to speak to the security folks.
what are we doing? So I think the most important thing is you know, as I said, is like we need the right APIs between operators and developers, whether it's, you know, the security guy, the networking guy, talking to developers. So that a developer can express their intent and you know, the security guy can use that intent and map it, you know, to the policies. And so I think Kubernetes or DCOS or Docker, right, everybody has ways that let users express that intent. I think in terms of implementations, we're using all the same things that have been used before, like VXLAN.
So
nothing new there.
I can take that a little bit, right? People screw up if it is complex, right? First of all, right? So the first important thing is make it simple, right? That will make it easy to understand and be more secure, for the matter. So if you look at Docker, the stack that I was trying to explain, the Docker network as a concept, object, it's a simple object. People look like, hey, Docker network create, it created a network, right? But actually network is an isolated entity, right? When you have a network create and you start attaching containers to that, those containers cannot talk to anything outside. They can, it's restricted to be talking only within the network. So everything that is taken care for isolating things is taken care by the platform. And we actually flip the thing where if a service wants to talk outside, they have to explicitly say, hey, this service needs to be exposed this port outside this network that is managed by the operator. So we are trying to make things simple, at the same time provide the isolation rules built in, right? Instead of having the users have to provide a policy rules and so on and so forth, it's actually the other way around. And of course, we have encrypted tunnels and encrypted control plane, data plane as well.
Yeah, I think Toby and Madhu hit it on the head that let your users express their intent in the simplest way possible that will satisfy your network or your security engineers. So Kubernetes has the network policy object, which it sounded like you guys might be using, where you can express the connectivity that you want to allow, let the implementation of that be handled by something that actually knows how to implement it in your system.
Yeah, and I will actually echo that. The way eBay is approaching this is that we're investing a lot in a policy-based engine, where you can describe the policy at an application level, and either at an edge level or at an intra-application level. And then the enforcement mechanisms can be different. And again, there's some convergence needs to happen, or like what are the right microsegmentation techniques. Of course, you can use SDN, but then there are solutions like, you know, companies like Illumio out there which are doing it at a higher level. So, I mean, from our perspective, it's an isolation problem, and we need to figure out what's the right technology to enforce it. I mean, it can be enforced at the application layer. It can be enforced at, you know, above the network, or it can be enforced on the SDN layer. I think all of those options are there, but I think, again, this is one of those places where there is not as much clarity on what's the right way, but we are picking something for ourselves. But that's where we are.
Super. Well, thank you so much. That was fantastic here. I learned a lot.